Now, we got to have another one as we go ready for the next thing, right? This is a great one, I think. Psychologically, one of the great powers of programming is the ability to define new compound operations in terms of old ones, and to do this over and over again, thus building up a vast repertoire of ever more complex operations. It is quite reminiscent of evolution, in which ever more complex molecules evolve out of less complex ones, in an ever upward spiral of complexity and creativity. And then it talks about likewise with programming in Lisp, only here the molecules are now Lisp functions defined in terms of previously known Lisp functions. All right, same thing, just replace the word programming in Lisp with programming in Fish, right? So I love this idea that you start with something, now that you have that weight balls function, you could use that function inside of another function as part of some more complicated logic, right? And these things just keep on building on each other. All right. Let's return to this problem now. Remember this one. Create a parallel bonded cantilever beam, apply a tip load, and monitor P delta. And we did that right here. If you recall, at the beginning of the class, the last class, we wrote code to do this, and we solved the problem for what it says in the title, cantilever beam with a tip load of 100 newtons, right? It's fully fixed on the left. They're parallel bonded together. We're applying right on the far right in the Y direction, a tip load of 100 as an applied force. And now we're cycling and we're taking a history of the Y displacement of this guy, and we're plotting that on the Y-axis versus the number of cycles. And you can see how it overshoots, and then the damping is going to remove the kinetic energy till we come to a single value. And we showed that, and here we did the ball list attribute displacement just for the tip ball, which is the one that has ID 11. And we were able to confirm that we're getting a very close answer compared to beam theory. Our displacement is 6.78 millimeters, and the beam theory is 6.79 millimeters. And we talked about part of the difference here is that this solution is a large strain solution. And for example, when you start to rotate this tip ball is actually moving a little bit to the left. That's why it has a non-zero X displacement. That would not be occurring in the analytical beam theory solution. And so you would expect there to be a slight difference between these two. Okay. Now, with that as the starting point, we need to do this. We need to write a function that we're going to call load beam, and it's going to take one parameter, which is the value of P, but P is going to be a sophisticated thing. This variable, this parameter P, is actually going to be a list of n values. Okay, so we're going to say, and if we did that, what we would expect then is if we gave, let's say this was 50, 100, 150, it should go, if we apply, and then again measure tip displacement versus step, this is P1, it should go a certain amount to delta, then it should go a certain amount, and then it should go a certain amount. So if we do that with this as the input, right, this is the answer we should get. Again, we would just be monitoring, it's the same history as before, except this time we need to write code. So inside the function called load beam, it's going to have to do this solve. It's going to have to apply the load, whatever it is. It's going to have to do the solve command with the ratio average, get to here. Then it's going to go and do the same thing again, but now it's going to make the load bigger, and it's going to do the solve command, and then it's going to do the load bigger again and do the solve command. So that suggests that we have a loop, okay? And the loop is going to go from 1 up to the number, the size of the list. And it's going to keep on taking the value out of the list and applying it to the tip and solving. So see if you have, let's see if we can do this. So do you should still have your previous thing here. What we did is we created a thing called load beam dash P equals 100 newtons. Okay. So here, just so that we all have the same thing that we're working with, okay, you're going to see this is going to be a quite small amount of code we're going to have to write to make this, because all the complicated stuff we already did. I want you to go into just if there's something you created, just rename it or something, either delete it or rename it. I'll put it called dash temp. I don't want to work with that. I want us all to work with the same starting point. So go into solved, and inside of solved are two directories. One of them is what we created together, which is load beam for one particular case where P is 100 newtons. So I want you to copy that directory, copy up to the top level here to the load beam. And you should have this. Okay. And then go inside here and fire it up and check that it's working and that we understand it. So now, and this is also a PFC 3D project. So I'm going to double click it. Here we go. I'm just going to run it. Then we'll go back and look at it to refresh our memories. So let's talk about this. What do we need to do for this code? We need to achieve this. And remember, we're going to end up writing a loop, right? And then we're going to do something inside the loop. So let's just get that part set up. All right. So what I want to do here is let's shut this down. Okay. Well, let's just talk about it. What I'm going to do is we're going to shut this down. We're going to make a whole new directory where the solution is going to be. We're going to copy this data file that works for a tip load of 100, and we're just going to modify it a little bit so that what it's going to do is it's going to just a second, let me look at my notes so I make sure I say this correctly here. We're going to modify it so that it does everything except it doesn't apply the tip load, because we're going to do that in the function that we're going to write, right? Because we have to do the different tip loads. So just follow along, do the same thing with me. So we go out here. So there's our example, load beam P equals 100. I'm going to make a new directory here, that same level, do the same thing. I'm going to call it load beam. This is going to be our actual solution. Okay. And the first thing I'm going to do, okay, I'm going to go into the P equal 100 directory, and I'll get rid of my save file. I'm going to copy both of these things. And I'm going to put them into load beam. And I'm going to copy this data file and I'm going to rename it, and I'm going to call it load beam dash, instead of P equal 100, I'm going to say dash initial. Okay. We're going to want to basically modify it so that all it does is set everything up, but doesn't actually give a load. Because that's what we're going to end up doing in the function we're going to write. So now open up in here now at this place, open up the load beam. And make sure that it works like before. So I'm just going to run it. Going to watch it here. The one thing I'm doing in this problem is I'm doing this solve ratio average to a very low number because I wanted to compare very carefully to the theoretical solution. You can see there's pretty much negligible change anymore as these cycles are going on. Now let's do call in that data file, the one that we created called initial. So you're going to go to the file and you're going to say open. And now you're going to choose load beam initial. Okay. And now we're going to modify it. Okay, so now line 3, we're going to change the title. So we're going to say cantilever beam with tip load unspecified. There we go. Now we're going to go down where we were right here on line 24, where we were applying the tip load. Just get rid of that line completely. We're not going to specify the tip load, but we're going to set everything else up. And then at the end, we're going to do a save. And we're going to call this thing load beam dash initial. So when this gets run, it's going to set up the whole problem, but it's not going to, and we're going to also take out lines 27 and 28. We don't want to actually run any cycles. This is just going to initialize the system. It's going to create the beam, set up our histories, do everything else. It's going to make a save file. Okay, so run this. And what should happen is there's our beam, there's our history, just like before. And notice it created a save file, load beam initial. Now let's just get rid of this other, let's close this other tab. We don't need it anymore. And let's also go up here to the load beam P equals 100 and just get rid of that from our project. We don't need it. So let's say remove from project, select it, give it the right finger and say remove from project. And we can also go to the saved states and that other saved state, the 100 Newton one, get rid of it, remove from project. Okay. And then we don't just want to remove it from the project just to clean everything up in our directory where we're working. Let's get rid of the equal 100 Newton data file. Let's get rid of all the save files. And now let's run this again, load beam initial. And now we should have a clean set of things. We have one data file, load beam initial. It made a save file. There it is. And we have the project. All right. Now we can actually write the code that's going to do this.
Yep.
Okay, let's write the code. File, here we go. New data file. New data file. Give it a name. We'll just call this one loadbeam.p3dat. Loadbeam.p3dat, and then hit return. So there we go. It's open in an editor. You can see the name. It's now in the list of data files. So let's do this together. So the first thing I always do is program return. That's going to be the end of the system of this thing. I'm going to restore the thing that I already created, which is load beam initial. There we go. So this data file assumes that you first ran load beam initial and produced the save file. Now the next step is we're running this guy, right? Okay. So now we're writing code, writing a fish function. This is what we're gonna do first to make sure stuff is making sense. Fish define, hello. io.out, hello world. And now call the function. Let's just run this. Just make sure this is working. Then we can continue on and actually write the function we're really gonna write. So I'm gonna run this. And I'm getting there it is. I ran the function, I called the function hello, and it kicked out to me, hello world. Okay, now let's write our function. And we go back up. Here's the specification. I said, make a function called load beam that takes in one parameter, which is a list of load values. So load beam takes in P. That's my function. And let's not worry about P right now. We know that we're going to have to write a loop. So let's do that. Loop local I. And let's just for now go from 1 to 3 and then do the end loop. Right? And let's just make sure this is working. So I'm going to say, I'm going to give the single the quote, and I'm going to say I equals space end of quote plus string I. And now we're going to do and make it even simpler. Let's get rid of there's no parameters, just a function called load beam and call the function. I'm going to get rid of this hello business. So if this is right, it's gonna say I equals 1, I equals 2, I equals 3. Boom, let's see. Here we go, load beam, I equals 1, 2, 3. Okay. Now we need to create that list that we're gonna feed in. So let's create that list. I'm gonna say square bracket. It's a global variable. Let's just to give it a different name, I'm gonna call it the P. And I'm gonna say equals list dot sequence of 3 values, 50, 100, 150. End square brackets, the P. And then to see if that's working, I'm going to say fish, list, contents. I think this is how I do it. And I'm going to put a return right there. So now it should actually give me that it's a list and it has those values. I'm going to run it. Oh, looking good here. Fish list contents, the P. It's a list. It has 3 elements. They're integers. Just what I want. I'm going to get rid of those 2 little testing lines. So now the parameter is going to be P. That's the name of the parameter that I can use inside the function. Okay. And now I don't go from 1 to 3. I go from 1 up to the size of the list. So this is going to be list.size of P. And so if this works, it should again go I equals 1, 2, 3. Oh, look, I got a bug. And what I do wrong? List that size of P. Loop local I. Incorrect number of arguments passed to symbol load beam. Oh, yeah, so this is good. So on line 12, I'm calling the function, but the function now takes a parameter. It's telling me it's not given. I didn't give it a parameter. So what's the parameter? What's the name of the parameter? It's the global thing that I created, the P. Now let's test it. Hey, I equals 1, 2, 3. Let's test it even more. Let's, instead of 150, now let's make it, now it should I equals, see, I added another thing to the list. Run it. I equals 1, 2, 3, 4. Hey, I think we're in business.
Morning.
Now, let's just do the simplest thing. So inside of here, I need to specify the applied load. And so I'm going to use the command called ball attribute force applied y. So if I'm going to use a command inside fish function, I need to I need to say command end command. Okay. Now what's the command going to be? It's going to be ball attribute. And now it's called force applied y. And now what's that force applied y? Well, it's going to be a fish variable. It's going to be P P of I. And I'm giving P as positive, so a force applied Y, I want it to be negative of P. So I'm going to put a negative, a dash, negative PI. And I only want to apply it to the tip load, tip ball. So I'm going to say range ID 11. So let me try to run this. So it told me attribute force applied Y initialized in one ball, and it did it 3 times. Now I want to cycle the thing. So let's just do model solve ratio average. And let's just do 1e minus 5. Close enough. And then after I'm done solving, I want to put a pause in there so that I can see what's happening. I can do it one at a time then. Applying the force based on the parameter that got passed in that list. And I'm taking the first element, second element, third, whatever. That's what I is. Solving it. So let me run this. So the first time through the loop, it applied the force and it's doing that solve. And then it's going to hit the pause. There, it hit the pause. Now I'm going to say continue, and it's going to do the second time through the loop, right? And what should happen is the tip displacement should get even bigger because we increase the load. Then the last one, and then continue again, and now we're done. The whole function is done. Notice that the title here is not correct. It says cantilever beam with tip load unspecified. What we want to do now is inside this loop, we want to set the title so that it says cantilever beam with tip load of whatever P is. Okay. So let's do that. So what we're going to have to do, so let's get this. We're going to create a local variable, and I'm going to call it title new equals. Let's just make it be Fred. And then in this command thing, I'm going to give the model title. Model title, what's the title? Square brackets, whatever title new is. And then do everything. Let's see if that works, and let's make it run fast. So instead of doing model solve, let's comment out model solve. Let's comment out pause. And instead, let's just do cycle 50. So when we run this, it should have changed the title every time. It should say Fred. So let's run this. There, Fred, every time. Okay. So now let's make it say what we want. So let's say cantilever beam with tip load of space, end of string, tip load of plus, what do we want to do? We want to turn it into a string. What are we going to turn into a string? Key of I. And then I'll say plus another string space n dot for newtons. See that? I'm building up a string, which is going to become the title. So let me run it. There, cantilever beam with tip load 150, because it ran through 3 times. So it was the last time is the one we saw, and that's when the load is 150. And the last thing we're going to do is every time we apply a load and get to equilibrium, we're going to make a save file. Okay. And we're going to call these save files, what are we going to call them? We're going to say load equals, the value 100 newtons. That'll be the save name. So here we're going to say another local variable, and I'll call this save name equals, and so I'm going to say load all one thing. Load equals end of string plus the string p of I plus the string n. Boom. Save name. Load equals 100n. Load equals 150n. And then I have to do the save command after we're done with the solve. Let's get rid of this thing. After I'm done with the solve, I'm now going to say model save. What am I saving? Save name. That's the name of it. Do a pause. Clean this up now. There. Okay, let's run and see if it works. This is the whole thing. Boom. There's the correct string, cantilever beam with tip load. Now after it gets to equilibrium, it should create a save file. And presto, continue, and look at it, made a save file. Load equal 50 newtons. Now I do continue, and now it's doing the next step. So we're illustrating a whole bunch of things here. This is an example of now we've set up this very powerful function, right? All I need to do is change the values in that list, right? The list can be any size because it's using the list itself to figure out what size it is. And we're building up a bunch of save files, right? You know, so when we do a triaxial test, for example, we're going to essentially, when you do a real triaxial test, what do you have to do? You have to turn on the confinement, and you need to set up the system so that the confinement is applied. And then you're saying, okay, now that's the beginning of my test, and I'm going to start moving the platens. So we're going to do the same thing. We're going to like set this thing up. It's going to apply the confinement, and it's going to make a save file. And then we're going to say run the test, and it's going to go. And then when it's done running the test, it'll make a save file, and we can build up the names of these save files using fish. Okay.